takes more time than I thought to write down the theorem.
The whole talk we should be writing down.
Yeah. Did you start already the recording?
Just now, yeah.
Oh, okay, good.
Okay, so welcome everyone to Amsterdam. Thank you all for coming to the third session of our seminar on mirror symmetry and modular space Higgs bundles. And it's a great pleasure to welcome Bas Edixhoven from Leiden, who's going to give the first talk today on Gerbes and stringy point counting.
Well, it's just section 2 of the article we have to go through, I think.
Yes.
And whatever the title is. It's about this theorem, and I was already writing it down. So the A was the first letter of assume. Assume. So there is mathematical statements are usually of the kind if-then, right? So we assume that for every surjection from R to K, so K finite field, the point counts are the same, and these are stringy point counts, and they take, oh, this is a 1, right? And then I have x1 of k, so that this is equal to the stringy point count of the other one. So x2 of k, maybe I put it, this is where the assumption stops. And then you have the same for the e polynomials. So the stringy e polynomial, and now the notation is x1 over c, because r is embedded into c, right? You can place change it to c with the data that we already have with respect to this, and with variables x and y. This is a polynomial in x and, well, almost. We will see stringy point count of the x2 base change to c with the alpha 2 as a gerb and xy. Okay, that is the theorem, and in this hour, minus 3 minutes, I will try to explain what these things are, actually. So my plan is to keep this on the blackboard and to use only the other parts to explain what it is. Okay? And this plays a role in the seminar, because what is the end goal of the seminar? That is to prove that two stacks have the same stringy e polynomial. And you see that this is a useful theorem if you can count. Right? And so I will not tell anything about where these xi come from when we apply them. We have seen the previous afternoon there was a lecture about that by Wessel. Is Wessel here? No? Oh, okay. Okay. And Wim Vijs gave a talk about e polynomials. This twisting had not yet occurred, I think. That is something that we will see this time. I have to go on, and I have 4 sheets, and I have 15 minutes for each. So, so I want to first, is there color chalk here?
Yes.
So, what is the first thing that you don't know, actually, here? If you look at the statement of the theorem, where should I start? I think up to here, everything is standard, right? No? Are there questions before that? Generically free action, so we know what the scheme is over. This R is clear, it is a subring of finite type of Z, of C.
But it's a bit odd to write that the order of gamma I sits in R.
Well, it's an integer, and the integers are contained in R. What I want to say is that it is invertible. So, and that helps a lot. If you do geometry over a ring, with schemes over that ring and with a group action, then it is a nice thing to know that the order of the group is invertible in the ring. Yeah? That allows you to project on invariance. So that is a good thing. So let's look. Are there other things that you want to complain about? This R is an integer,
Yes.
positive, and it is also invertible in the ring.
In the bigger ring.
In that ring, yeah. And I have a mu R gerb, so that is actually what are the terms that I have to explain.
So
I
the
think
gen is it generically free or
generically free. So there is a dense open part.
Yeah, I know, but I didn't know what Chen.
I know, but I wanted to keep this on 3 lines, and that, you see that it was absolutely necessary. I think this needs to be explained. Well, this is also clear that you have these, right? Every maximal ideal of R is a finite index. You get many closed points of the spectrum. I think this also has to be explained, what that is. And also this, right? And if I explain all these things, then I hope you are happy. Okay, good. So I'll do my best. First, this stacky quotient, right? So I simplified by a factor 2 the explanation, because here there is a symmetry between 1 and 2. Yes, Peter?
One question: does the ring homomorphism for RTK have to be surjective, or do you want it also for extensions of residual fields?
That's a good thing. Okay, good. That's a very good. I want it also, of course, for all extensions, because I want zeta functions and so not surjective. Yeah, good. That is a good thing. Good correction. Yeah. But for the work, it's absolutely the same. So okay, good. So stacky quotient. So here I put myself. I have a scheme or a variety, if you like, of that kind, and nice. And I have a group, finite group gamma acting on it, and I want to take this kind of quotient. And I want to. So who knows the definition of this?
Well.
Yeah, I know. So not everybody. And you can look up the definition, but I think it's also nice to know where that comes from. So S0 any scheme, and I take X over S0 a scheme. Okay, and G an affine S0 group scheme. And I think actually in that context it doesn't cost anything more to explain what such a stacky quotient is. So then I would like to do here a G, right? And in that situation. Okay, so and actually I wanted that my X acts on the right. So actually that means that for every S over S0, I have the S points with an action of the S points of S, right? And now I take the quotient, and this is functorial in S, let me say that. And what I do is we let X of S divided by G of S with these brackets be what it should be. So what is this? This is a category with objects, this set, and with morphisms, we have triples, X, Y, G, where X and Y, well actually I would say in X of S times X of S times G of S, such that X times G is Y. Right? And if you like pictures, you could picture a morphism like an arrow. You have an object X, you have a G, and it brings it to a Y. And you can compose, right? It is a category because we have a group action. Everything clear? And this is a category in which every morphism is an isomorphism, so that's called a groupoid. And and this thing is functorial in S, right? For every S prime to S, we get a functor. So actually these X's and so on are contravariant. Huh? So we get X of S mod G of S in this sense to X of S prime mod G of S prime in that sense, because and this has a name. Oh, yeah, we can also say this map here, if this map is called F, I call this F upper star. We have pullbacks. Okay? And this this is our way to take the quotient, so actually you should say, have you taken the quotient, say this is a group acting on a set, in what sense did I take the quotient? Well, the orbits correspond to isomorphism classes. Right, so if I take what you call the pi zero of that groupoid, then I get my quotient. But I also have these morphisms, and that is a good thing. So that is the idea is to take the quotient, you shouldn't do anything, you should just write it down differently. That's what happened. But this is not the definition of this, right? Because you see, that there is, I would like to take the S points of this, but that's not the same as this. And that is because you have to sheafify to do this. So here we have a pre-sheaf in groupoids, right? Groupoids on S0, right? Or yeah. And well, actually, if you want, schemes over S0, right? That is a category, you can do that. It's a contravariant functor on that. But it takes values in categories, right? I mean groupoids. And we want to sheafify it. It needs to be sheafified. And that is so. So how do I do that? So when I sheafify, I also have to introduce a topology. Let's say for the on schemes over S0 with the étal topology. You can take any topology you like, but this is a usual one, or FPPF, say. Okay. So, but I have so for every x, well, for every s over S0 and for every x and y, we can look at the hom from x and y in this category, also after pullback, and that is already a sheaf, right? And instead of hom, I write isom, and this is a schemes over S now, to sets. And you can, what does it do? If I have a scheme over S, I can pull back these things to T. If I have T to S, I can pull them back to T, and I can look at the morphisms in that category where S is replaced by T. And that gives me a functor to sets, and this is already a sheaf. And in view of the time, I'm not going to explain why, but it is basically because the G is a scheme, and a scheme as a pre-sheaf is a sheaf for such a topology. Right, so that is a good thing. So the problem is with the objects. However, not all descent data for objects are effective. And so, in view of the time, I'll skip. I will put my notes on my homepage. So if you want to see that, you can look there. I could write down what is such a descent datum in this case, but so I can better, maybe it's just shorter to write down the outcome, because I don't think I should take much time for that. Well, actually, no, I can do it. It's because it occupies half of page 2, so I have 7 minutes more. Okay, good. So let me do it. So I want to explain that, right? So what is a descent datum? Let S prime to S be étal surjective, and X in X of S prime. Right, so I have in categorical language an object in my category over S prime, and now I want to know what is a descent datum, and I want to show that the descent gives something that does not usually come from an element in X of S. And we see what it is, and that's a very useful thing. So a descent datum to S is, for this object X, by this map S prime to S, what is it? For every V, so for every diagram like this, I write here I have a map S1 and a map S2 with the same composition to S, right? So you should read that as 2 points in the fiber, in the same fiber of S prime over S, right? 2 points in that fiber. I want to do something. I should have a given G in the group, which depends on S1, S2, in G of V, right? Because these are V points of G, such that, and now I want to write S1 upper star of X times G S1, S2 is the S2 upper star of X, right? And this is an identity in X of V, right? Yeah, I want that, but it should also be compatible, because if I want to descend some object on a point of this, well, on this whole phi, on this whole S prime down, so now I know how to identify 2 given things, but if I have 3 of them, you know, then there can be a problem. So, such that for every, well, say S1, S2, S3, you want that the G S1, S3 is equal to the G S1, S2 times the G S2, S3. Right? That is because the morphisms in my category are the elements of G, right? G with a target, a source and a target. But this is something that should hold not in the set, but in G of V. Right? That is a descent datum. And now I have to switch to the other word. So yeah, it will disappear from your site, unfortunately. But you can look at that on the television later, on your computer. So, so with this descent datum, with such a descent datum, we can, so here comes the whole thing, we can descend an orbit map, and that is of X. So what is this orbit map? That is this. I have G over S prime goes to X over S prime, and that sends, say, G to X dot G. If you take, so this I call X dot. And you should do this after taking points in an S prime scheme. We can descend this to S, giving the following kind of datum, a T to S, and a map from T to X over S, X. So this should be GS equivariant, and this should be a GS torsor. Right. Well, this has a right action, so it only makes sense with a right action. Okay, that is what I want to say. And do you want to see it? I have time, I think. So maybe it's good to spell this out. So what do? I write down how it works. This descent for the torsor for the orbit map. If I have if I have 3 of these things, S1, S2, S3 to my S prime, all over in the same fiber, I write down this map here to XV, and this is the S1 upper star X, the orbit map of that, right? I have the orbit map of the S2 upper star X, and I have the orbit map of the S3 upper star of X. And here, now I only need to write down which are my isomorphisms between these orbit maps. And here you see that S2 was S1 multiplied on the right by this G element. So here I must multiply by the inverse, right? And that's also logical because my G action was from the right, but here I get something on the left. So it couldn't be anything else, right? G of S1, S2 inverse multiplying on the left. And here you see that it works now, right? Because here I put G S2, S3 inverse multiplying on the right, and this is compatible with what we have there, right? So yeah, I think that's nice to know, right? technical question. Why did I ask that the G was affine?
Descent data for the scheme.
Yeah, I said I do schemes, right? So I want to descend this orbit map here, this GV should descend to a scheme T. And if I want descent to be effective for schemes, I better ask that the group scheme is affine. And if you don't want it to be affine, then you have no option. You should only ask that T is an algebraic space or a sheaf, right? Okay, so it can be much more general, but you have to pay in the shape, in what T is allowed to be. Okay, good. So then we can define. Now I can define my quotient then. Oh, can I? Yeah, I think I want to do that. Quotient to this stacky quotient. X mod G of S will be a category. Category with objects, and I'm very lucky. These. And what are the morphisms? Well, if you have another one, say T1, T2, also like this, then here is your morphism, right? These are the morphisms. Yeah? So that's now, yeah.
Could you also take your G to be projective if you keep track of an ample line model? Because descent data is also a vector for projection.
But my group scheme is affine, so everything
Sure.
is fine.
But you asking why, I mean, if your G was projective instead, that would also work.
No, it wouldn't work.
Okay.
And is Wouter here? No. he made a nice, well, there are counterexamples. So torsors over abelian schemes are sometimes not representable.
Yep, you're right.
So it is and you wanted a projective group, so yeah, that goes wrong. Okay. Okay, so I have this quotient now. Again, I have to see how much I want to do. Yeah, so what is this quotient map? I mean, for every S I have here, this is a set, and I want to map it to a category, right? So there is no other option than to make this set into a category, so as objects, plus only identities as morphisms, right? And then you have a functor. And indeed, this functor takes the quotient in the sense that points that are identified by the group action go to isomorphic things there. And this map is universal for that property. But also, I sheafified it, right? That is a good thing. So, okay, good. This is a good example of a stack. A stack, this is our first example of a stack over, so this is a stack.
So did you say explicitly what the G torsor you get is? From a
Yes,
point?
because I said you have to descend this orbit map.
Okay, right. Okay.
Yeah, that is what it gives, whatever it is.
Okay,
but
yeah.
but I told you how it is logical that it is such a thing.
But in this case, you'll get this map will be like the trivial torsor. The quotient map will be taking the trivial torsor, right?
No, because you see the torsor, it's a right torsor, and here I do, and any torsor becomes trivial after on some locally. So there is no reason that the descent of a trivial torsor gives you a trivial torsor. Why do you think it's trivial?
But somehow, I guess, only because I'm like, for every
You
object
see?
I should associate a torsor and some distinguished torsor, and so what else could it?
Well, but this map, no, there is, this is just an arbitrary co-cycle. So I can get any...
No, but I mean, sorry, for the map from, the quotient map from x of s to x mod g of s,
Yeah,
I said to every object I should give a torsor.
yeah, and that's okay,
That
yes,
one
I can tell you what this thing
Is
does.
that not the trivial torsor?
It does this, right? It gives you, so x here goes to g over s, orbit map of that thing, right? If you like. Yeah, I can remove this s, I think that's what I did, right? And then this to s, and that is your trivial torsor.
Yeah.
Yeah, so indeed, so now I understand your remark, yeah. So the things that correspond to trivial torsors are exactly the ones that come from here. Yeah, okay, good. So this is a stack, this x mod g is called a stack over schemes over S0 given a tile topology. And now I want to say a little bit about general stacks, but this is not supposed to be a very short crash course in stacks. I think I have to explain what this theorem does, right? So I don't want to. So yeah, why do I do that actually? These general things on stacks. Well, let me take 5 minutes to do a bit, and then you'll see. So a general stack looks like this. You have a category. You have another category. Well, this must be a site. This is a category with a Grothendieck topology, right? That here we had this one. Here I have a functor. And there are some conditions, right? So for every S in C, for every object in the base, we have this fiber category, and that fiber category has objects X in X with P of X is C, is S, that thing. And morphisms, yeah, that is good to say. You have X, F to Y, such that P of F is the identity of X, of S. Right? So in the fiber category, you don't do morphisms on the base. Right? That is an important thing. And then there should be this pullback. So there should be a Cartesianity, can you say that? Yes. What is better?
If you write it in a Gerbes after it becomes
for every, if I have a diagram here, T to S in the here, and I have an X that is mapped by P to S, right? So this is there should be a universal way to make a diagram like this, right? Here I have my T to S, here I have P, here I have also that should go to that, and this should go to that. And it should be universal, right? So that looks very much like a fiber product. This is really a Cartesianist thing. And if you have that, then let us pause for a moment. For every S, X of S is a groupoid. That is a formal consequence of this. So all the morphisms in such a fiber category are isomorphisms. And we also have after some choice, F star, well, if we have pullbacks. If we have F from S prime to S, we have F from X, S to X, S prime. We can do pullbacks just as in the case I showed before. This is a choice, but nobody has to care about it. Nobody should care. And that up to here, this is called a pre-stack. And so, as you see, because in my example, this fiber-wise stack equation, still somewhere I think, when I took X of S divided by G of S, that satisfies up to here all the conditions. So for the stack, the following must hold. One is that for every S in C, for every XY in the fiber category, the isom functor from X to Y is a sheaf. Sheaf on C over S, right? That is a. And secondly, all descent data for objects are effective. And I'm not going to write down again what a descent datum is, but it's the same as what I did. So that's well then. Yeah, maybe I go to the board. So these stacks, to make it even more complicated, we are going to look at morphisms between stacks. because we need to. We have already seen an example. This quotient morphism from my x to x mod g, stacky x mod g, was also a morphism of stacks. And I said it had a universal property, so actually I was already doing that. So stacks form a two category. Stacks with a form two category. What does that mean? We have diagrams like this, x to y over c. Right here we have one as before, I have a second one, and here I have an f. And such a f is just a functor such that the diagram commutes. Right? So this is a commutative diagram. That's and I also have two morphisms. So if I have two of these, say x and y, and I have an f1 and an f2, then I can make a morphism of functors, and that's a two morphism. So these are called one morphisms, and these are called two morphisms. So this diagram does not commute necessarily, but there is an isomorphism between these two, because actually any morphism from such a functor to that is actually consists of morphisms in fiber categories of y, and so it's an isomorphism because my fiber categories are groupoids. Right, so these two morphisms are isomorphisms. That is an easy thing. And so I give you an exercise. That is Yoneda for stacks. It's good to do that. Yoneda tells you that C, the base category, the side, can be mapped to stacks over C by the thing that I did. If you have an object here, it gives you sets, but you can upgrade the sets to categories by just putting identity morphisms, and then you have your Yoneda thing here. Right, so I will freely use that now. And maybe you should make a little assumption that in this site, every object should be a sheaf, right, for that topology. That is, if you take too strong a topology, it's not good. But on schemes, you can do etal, FPPF, FPQC. Okay. Now I skip a few lines from my notes. I wanted to do fiber products in the category of stacks, but they are what you think. And if we need it, you can ask me about it. But okay, yeah. Okay, so actually, putting these base objects in the category of stacks makes it possible to talk about morphisms from schemes or varieties to stacks. And I wanted to say what a delineant-Mumford stack was, but I'm not going to. But I want to say that I'm almost. Here was my X mod gamma. Right here, I had a complex variety modulo a finite group. So that is X to X mod gamma, and the notation should tell you what I mean. This is, as a morphism of stacks, is etal, and actually it's a gamma torso. And I don't have time to say much what that means, but it means that if you take another object from the base and you map it to this, then the fiber product exists and is a scheme and is of this kind. That is the whole philosophy. And so you can say geometric things. So up to now I talked about these stacks as a kind of sheaves of groupoids, but you can also do geometry with them if they are good. And so this makes this thing into a delineant-Mumford stack. Okay? And that's also not so very important. What is actually more important is that we can not only do geometry on this, we can do also sheaves. So sheaves, because you see, I have to go to these E polynomials. So I need to take cohomology. So I need sheaves and cohomology. And that is just a general thing that works. So what are sheaves on X with gamma? These are gamma equivariant, so sheaves with a gamma action. Variant sheaves on sheaves F, say, on X. Well, with a topology, say étal, right? Or Zariski, if they are sheaves for the Zariski topology. Yeah, it makes more sense to do étal. Okay. And cohomology is also very easy. Cohomology derived functors of F goes to, well, I can take the global sections and then the gamma invariance, right? That's the, you take derived from, this is a left exact because composition of two left exact. We are happy, lucky, I mean. You can take, also the usual spectral sequence works here, right? You have, it's a succession of two functors, so you can first derive for the, well, you can apply the F, and then there is a Leray spectral sequence for that. And actually, you see also that the condition that the order of the group is invertible on the base is now, has a very nice consequence, because that means that taking the gamma invariance is, well, if the, if I think of coherent sheaves, then that is an exact thing. Because coherent sheaves are sheaves of modules over some ring, which is an extension of this R. And if the order of gamma is invertible in R, it is invertible in any other R algebra. And if I think of étal cohomology of some analytic sheaf, then maybe I should take QL coefficients and not ZL coefficients. I want this to be exact. I don't want to worry about group cohomology, right? Not now. Okay. Well, things are going fine, I think. So then we come to the Gerbes, right? There was also a difficult word here. So actually maybe I should keep track of what I have done. This is okay. And the next thing is indeed the Gerbes. Okay, Gerbes. Well, maybe that merits another blackboard, right? Okay. So you know that H1 of a group sheaf, of a sheaf of groups, can be described in terms of G torsors, right? If your sheaf is called G, then the H1 is the set of isomorphism classes of G torsors. And now we want to do H2. And so that the answer is Gerbes. So, but then, okay, so that's alpha being H2 of my X with UR, right? So this makes sense now. I told you how to do that. Well, maybe R is also, oh, R was also invertible on the base. Yeah, so I really told you. Yeah. Okay, so this gives, yeah, so what do I want to say? That gives, by the formalism of Gerbes, a mu R gerb, and let's say G to X. So actually, I was used to work with such things on a scheme, but on a stack it's a bit different. It's a bit more difficult, but I think also in Peter's talk we will see things like this, right?
Yeah, some at the end.
Yeah, okay. So I will try to say what it is, such a thing. Well, it's a morphism of stacks, right? So let's say that this is a F here. So this is a morphism, a one morphism of stacks over, actually, yeah, over the base over which we work. So that could be the complex numbers now, right? And so, yeah, such that, okay, such that I have this, I have to copy it again. If I have an S in my base and I have an object here, then I get a fiber category here, right? This is GX, so fiber category. Do I want to, that is, I want to not to take the fiber category as I did before. I want to say that I can still, I base change it as a stack, so I can still apply base change on S to that. Yeah. So this, but now I have something over a scheme, and this should be. So what does I want to say? Locally on S, it has an object. So for so you can find a cover of S by SI's such that the G of SI is not empty, and any two objects are locally isomorphic. That's a gerb.
So is this for all S to X? Schemes?
For all S to X, I want to have that, and it's not yet finished. the conditions. But this is something that at least if you work over a scheme and not over a stack, then that is what you call a gerb. And actually here it says mu R gerb, so that is a bit more complicated. And in this case we want the objects are that and all out x's, right, are compatibly well are given well there is and this is isomorphic to mu R over S if I have x in G of S. And this is a given isomorphism, and it is compatible with isomorphisms in that category, right? So that should be just a that is. And now, if you look at the effect that you work over a stack here, you get something like this. If you have a y, so here we have x in x of S, and you could take the y in G of S over it here, and that means that oh yeah, maybe I should have called this y, huh? Y, but this is over X. So these are the automorphisms of such an object that induce the identity here, right? And but when I also look at possible automorphisms of X itself, then there is more. So you want. You have, so there is a condition. So I have mu R over S inside out of this Y, and that maps to surjectively to out of X, and this should be a central extension. That is the condition. Yeah? And I can give you an example, maybe that's a good thing. And I could ask you, what do you prefer, geometry or algebra? Should I give a geometrical example? We take, so what should I take? So we take, I will just write down all the things, schemes, right, with the étale topology. Here I take, for X, I take the moduli space of curves of genus 0, right? So these are genus 0 curves, projective, well, smooth projective, yes. Well, in some sense projective. And over that, so here the objects are, here I have object schemes, here I have, say, C over S a curve of genus 0, and here, in this G here, from my gerb, I take line bundles. Here I take C over S, and the line bundle, so this L should be an invertible OC module, fiber-wise, degree 1. And if you think about what this group extension is now going to be, here, so there is an object, right? I mean, you can say, well, I know a curve of genus 0, P1, and I know a line bundle. And if you write down what these automorphism groups then are, oh, then you see here the GM, the multiplicative group. Those are the automorphisms of the line bundle that give well, here, identity automorphism of line bundle. But here you have PGL2 for the P2, for the P1. So actually that gives you the very familiar GL2, PGL2, GM central extension, right? And you could also do this, but not. There are also genus 0 curves that do not have such an L, right? Like if you take a conic over a field with the conic has no rational point, then there is no such a thing. And so that means that is exactly this. Local, so you have objects here that locally, for locally there exists such an L, but not globally. And that is actually the correspondence with the H2. Because if you try to lift a co-cycle, well, what do I want to say? The H2. So the H2 is given by two co-cycles. And actually that arises if you have a torsor. So such a P1 bundle is a twist of P1. And so you can describe it by a PGL1 torsor, PGL2 torsor. And if you want to have on your twist a line bundle, then you would want to lift that one co-cycle, or that torsor, to a GL2 torsor. Then you would have a line bundle. So the obstruction against that is in the H2 of this. That's very logical, right? H1, H1, H2, huh? So that's how that works. I lost a few minutes there, but I did something. I can cross out another of my to-dos. Right? The gerb, I hope you are to your satisfaction. We did that. I still have 10 minutes only. Ooh. But I have two things to do still, right? Stringy E polynomials and stringy twisted point counts. Okay, good. So I should talk about something that is called fermionic shift. I have no idea who it's not by Fermi, I think. So now we do X over C smooth. Right? So in the theorem it was not smooth. So actually I'm a bit worried about the theorem. Maybe you should also ask smooth. But I checked before my lecture that really smooth is not in the theorem. Okay, good. And we take with an X is X mod gamma. We take such a stacky quotient. And yeah, there is something to say. For every X in X, we have, if I look at the pair, at the pointed space, right, then I have automorphisms here, then I have an action of the stabilizer of this point. And this action can be linearized in tau locally, or formally if you want. That means that this is isomorphic, at least at the level of complete local rings, to a power series ring with an action, linear action on the coordinates. And that tells you something that for example, the fixed points, that's a smooth variety. Right? So, so for every gamma in gamma, the fixed point locus, this is my notation for the fixed point locus, this is also smooth. It's a smooth variety. So it is the disjoint union of its connected irreducible components, right? The other one was a tautology. But you can say a bit more. You can also say that if you take the tangent space of such a thing, then this is the tangent space of the fixed point locus, direct sum, the direct sum, well, the non-trivial isotypical components for the action, for the gamma x action, right? Or for the gamma action, if I take the group generated by that, right? So I can, as I said, I can linearize, but I am only looking at the action of a cyclic group, so it's very simple. On the tangent space, I have trivial characters and non-trivial characters. The trivial characters are exactly, that's the tangent space of the fixed point locus. It's a smooth variety, and I'm interested in the normal bundle with its action. Okay, so let zeta, I get some roots of unity, gamma x 1 up to zeta gamma x d. D is the dimension of x. The eigenvalues